Hi, it's early September of 2019. The school year has started here at Bethel University as at many other schools. I'm getting back into the swing of things in teaching after my sabbatical has now finished. And that means I'm getting back to teaching classes. That means I have less time for blog posts like my linear algebra textbook. But I am going to make plenty of shorter blog posts here in the coming months because I'm going to be videotaping Calculus 1 lectures and posting short blog posts about those lectures that you can use to review what's in those lectures. But I did just last week finish what's going to be the last section of Chapter 1 of my online linear algebra textbook. Ad infinity is really big here. It's section 1.10. The title is The Determinant of a Matrix. During the fall here, I hope to maybe write one or two more sections, starting new sections for Chapter 2. Chapter 2 is going to get more abstract, talking about vector spaces, and in particular the important idea of a basis of a vector space. So I'm going to start talking about linear independence and spanning more, but again, I won't be able to post as often then about linear algebra, more about calculus here in coming months. So let's go ahead and give the overview of this section. This section is an interesting mix of both geometry and computation. I try to, as I do in my Visual Linear Algebra online textbook, emphasize the geometry, the pictures that you can make with these things, but there are, of course, computations that have to be done, kind of messy computations, so you're probably going to want to have a calculator and a pencil and paper handy to check the calculations that you see as I go through this, or you can go to the blog post yourself. But yeah, if you're watching the video, go ahead and pause and double check calculations. As usual, I try to give insight about details and big picture here. So first I just talk about mathematical beauty, and usually if you've talked to somebody who's taken a linear algebra course, when they hear the word determinant, they don't think beautiful, okay? But determinants actually are kind of beautiful, and this picture is actually the main key for seeing that beauty, at least in low dimensions, in 2 dimensions. What you see here is a parallelogram in white, and you see it bounded by some vectors, 2 copies of the vector v and 2 copies of the vector w. And it turns out that the area of that parallelogram is the determinant of the matrix formed by putting v and w in the columns of a 2 by 2 matrix with v first and w second. And it is important that it's oriented in this picture in the way that you see to make the sign work out right. I talk about that here. This is the description of what I just told you. In general, it's actually the absolute value of the determinant because it's possible that the picture is not what you're seeing, but in this particular picture that determinant will be positive, and it does give the area of the parallelogram as I say here. Why is this considered to be beautiful? Why do I consider it to be beautiful, at least? In large part, it's because it's both simple and surprising. Okay, that's actually a key feature of things that are beautiful in math, when they are simple but surprising. For example, the Pythagorean theorem is simple and surprising. Now, you're kind of so used to the Pythagorean theorem that you don't think of it as surprising, but it really is if you think about it. If you never had heard of the Pythagorean theorem your whole life and somebody told you it was true for the first time, you'd probably be pretty surprised that it was true. Another reason it's beautiful is that it's got a simple and intriguing derivation. The same picture that I showed you a minute ago right here. Essentially, to derive the formula, you treat the area of the parallelogram in white that you see as the area of the rectangle that surrounds the parallelogram minus the area of the shaded regions that you see. And those shaded regions are made up of 4 triangles and 2 rectangles. And those triangles you can see come in pairs that are congruent to each other and have the same area. And the calculation is down here. Here's the key thing right here, to verify that, at least in the case where A is bigger than B and C is less than D, that we get the area being AD minus BC, which is the determinant, which does equal the absolute value of the determinant in that case. In the case where the determinant is negative, this case, the area ends up equaling this, which is the opposite of the determinant. In general, then, the area does equal the absolute value of the determinant. Is it possible for that area to be 0? Yeah, it's actually possible because v and w could be parallel to each other, and if that's the case, the parallelogram would get flattened. It would really be just a line, and it would have 0 area, and that's what I talk about right here. It would be a degenerate parallelogram. You can think about this in terms of linear transformations as well. Chapter 1 of my book here, I emphasize linear transformations a lot, as you know if you've been reading it. Consider a linear transformation, T, from R2 to itself, defined by the formula T of x equals A times x, where A is a 2 by 2 matrix. Suppose S is a nice set whose area exists. I don't want to get into the details about what it means for the area to exist. That's the topic of measure theory, which is a graduate school level topic. Though you could think about it more intuitively in terms of basic calculus if you think of S's, for example, being the region under the graph of a continuous function, you know from calculus that the area will exist. In this setting, the area of the image, T of S, is related in an elegant way to the area of S. It's the absolute value of the determinant of the matrix times the area of S. Okay? If you think about this visually, sometimes, and in fact in a visual that I'm about to show you, the region will undergo some sort of flipping, at least seemingly, in 2 dimensions as it gets transformed to its image, T of S. And in that case, you can sort of consider the image to have a signed area, which would be negative, signed, S-I-G-N-E-D, like I talk about down here. And you could get rid of the absolute value sign, and you could say the signed area, which will be negative in that case, is the determinant of the matrix times the area, where you think of this area as being positive and the determinant in that case being negative. Okay? Now you might wonder, is it a good idea to talk about signed areas? Well, it is something that's worthwhile sometimes talking about in math, as in calculus, for example. When you think about integrals where the graph goes below the axis, then you think in terms of signed areas that can be positive or negative. Here's an example in a visual. This matrix happens to have a negative determinant, so the regions will undergo some sort of flipping like you see in this animation as the transformation gets applied. As this animation parameter lambda changes from 0 to 1, we see this 5-petaled flower region getting transformed to another 5-petaled flower region from red to blue that undergoes seemingly some sort of flipping, almost as if it's coming out into a 3rd dimension at you. Now, I'm not being precise about what flipping means, other than just to see what it means here visually. We're going to go on to some algebraic properties of determinants. This is less visual, but important. And the algebraic properties I'm going to look at here are for 2 by 2 matrices. Those are the easiest to verify these things for, but they do apply to higher dimensional square matrices, meaning same number of rows as columns, 3 by 3, 4 by 4, 5 by 5, 6 by 6. They all extend to higher dimensions. I'm not going to prove these properties for higher dimensions. We are going to take that as just a given without proof. But we can see how it works for 2 dimensions, 2 by 2. In the exercises, I have the reader verified for 3 by 3 matrices, but the computations are messier. Before we can talk about the properties, it's worth giving a couple definitions. An upper triangular matrix that's 2 by 2 is of this form. There must be a 0 in the lower left corner, which ends up meaning that in the upper right part of the matrix, there's sort of a triangle shape of possibly non-zero numbers. That's why it's called upper triangular. A lower triangular kind of flips it. The 0 must be in the upper right corner, and the possibly non-zero numbers form a triangle shape in the lower left corner. Those numbers could be 0, but they don't have to be, and that's why it's called lower triangular. You might wonder, can we say an upper triangular matrix includes one where there's a 0 in the lower right corner, and a lower triangular matrix includes one where there's a 0 in the upper left corner? Actually, no, we don't make those definitions. There are good reasons for that. A triangular matrix overall is one that's either upper triangular or lower triangular. And we have the following theorem, which is so easy to prove it's almost not worth being called a theorem, but I'm going to call it a theorem anyway. Theorem 1.10.1, the determinant of a triangular matrix, whether it's upper triangular or lower triangular, is the product of the entries along the main diagonal from upper left to lower right. That's called the main diagonal of the matrix. So you can see it here, and this just follows easily from the formula for the determinant of a 2 by 2 matrix as the product of the entries along the main diagonal minus the product of the entries along the off diagonal, or non-main diagonal. Next, we want to see how determinants behave under elementary row operations. Remember that elementary row operations include interchanging 2 rows. They include multiplying a row by a constant. You'd really want to multiply by a non-zero constant, actually, for it to be an elementary row operation. And they also include what I call the row replacement operation, where you multiply a certain row by a constant and add it to a different row, and then replace that different row with the result. You see from this computation here that if you interchange two rows, it multiplies the determinant of the original matrix by -1 for the determinant of the new matrix. If you multiply a row by a constant, like the first row by the constant lambda, then the determinant of the new matrix is lambda times the determinant of the original. Same kind of thing happens if you multiply the second row by lambda. That's going to generalize to higher dimensions as well. It wouldn't really make sense to do that when lambda is 0. It's really not an elementary row operation then, but this formula still works even when lambda is 0. Note that this also means that if you multiply all the rows by lambda, the determinant of the new matrix is going to be lambda squared times the determinant of the original. This new matrix is often denoted by lambda times A, where this is really new notation. Lambda times A really means multiply the scalar lambda times the entire matrix A, which means multiply every entry of the matrix by A. This is standard notation. This generalizes to higher dimensions as well, though the power of lambda is not always 2. It's got to be the same as the dimension of the matrix, the number of rows and the number of columns. So for a 3 by 3 matrix, it would be lambda cubed. If it was a 4 by 4 matrix, it would be lambda to the 4th power, etc. Here's the row replacement verification. Actually, row replacement leaves the determinant unchanged. That's kind of amazing when you think about it. You would not expect that to happen. If, for example, we multiply the first row of A by lambda and add it to the second row and replace that second row, we get this new matrix, and you can just check by computation that the determinant of the new matrix is the same as the determinant of the original matrix. And the same thing happens if you do it a row replacement operation by multiplying the second row of A by lambda and adding it to the first row and replacing. Once again, the determinant is unchanged. That's kind of an amazing thing. You would not expect that, I think. I would not expect that ahead of time. It's also important to know that the determinant of the product of two matrices is related to the determinants of the matrices themselves, the factors. In fact, if you think in terms of linear transformation, and maybe pause the video and try to think of this on your own, the determinant of the product of the two matrices A and B should be the product of the determinants of A and B, determinant of A times determinant of B. Think of it in terms of linear transformations. All right, are you back? Did you pause the video and think about it? This is a description of why that's the case. Let A and B define two linear transformations, S and T. Think about their composition. As we saw a couple sections ago, the matrix for the composed function is A times B. That's a motivation for why we define A times B in the way we do. And by what we said 5 minutes ago, the signed area of the image is going to be the determinant of the product times the area of the original set. But if you think of that step by step, think about first transforming X by the linear transformation T, whose matrix is B. The signed area of the result is going to be the determinant of B times the area of that original thing. And then the signed area, when you now apply S to the new set, is going to be the determinant of A times this thing, which is really, again, the signed area of the image of X under T. And that, just by properties of multiplication, is the same as this. So these two things, here and here, must be equal. So the determinants in front of them must be equal. This must be true. You can certainly confirm this entry by entry by the formula for the determinant. If you multiply A and B, you get this. Therefore, you get this for the determinant, which expands to this. On the other hand, if you multiply these determinants, you get the same thing. Okay? Using mathematical induction, I didn't make this an exercise right now, but maybe I will make it an exercise later. You can show that this generalizes to any finite number of 2 by 2 matrices, and actually it will generalize to higher dimensions as well. The determinant of A1 times A2 through, say, AM is determinant of A1 times determinant of A2 times etc. through the determinant of AM. It's also important to note that the determinant of the identity matrix is 1, and therefore if A is invertible, because of this property, 1 is the determinant of the identity is A inverse times A, and the property says that's the same as the determinant of A inverse times the determinant of A, and we can now solve for the determinant of A inverse by dividing both sides by the determinant of A, and get this equation. That was quite a mouthful there. The determinant of A inverse is the reciprocal, the multiplicative inverse of the determinant of A when A is invertible. Once again, all these facts generalize to higher dimensions, and that's what I summarize here in this section. I talk about upper triangular matrices in general, lower triangular, and triangular. An upper triangular matrix in general for n by n matrix has all zeros below its main diagonal. A lower triangular matrix has all zeros above its main diagonal, and a triangular matrix is either upper triangular or lower triangular. Actually, a matrix that's both upper triangular and lower triangular, meaning zeros below and zeros above the main diagonal, I guess it's this way for you, is called a diagonal matrix, but I don't actually make that definition here. So here's the main theorem that I'm not proving. I did prove it in the case where n is 2. Exercises prove it when n is 3. For a square n by n matrix, the following facts are true. The determinant of a triangular matrix is the product of the entries along the main diagonal, from upper left to lower right. Interchanging two rows multiplies the determinant by -1. Multiplying a row by a constant multiplies the determinant by that same constant, though again that's only an elementary row operation when the constant is non-zero. Performing, this is the most amazing one, the row replacement row operation leaves the determinant unchanged. So multiplying a row by any constant, adding it to a second row, and replacing that second row with the result doesn't change the determinant. The determinant of a finite number of n by n matrices is the product of their individual determinants, and the determinant of the inverse matrix of an invertible matrix is the multiplicative inverse of the determinant of the original matrix when it's invertible. Part C also implies that if A is n by n and lambda is a scalar, meaning a number, then the determinant of lambda times A, where you multiply all the entries of A by lambda, is lambda to the nth power times the determinant of A. This theorem is actually useful. It's more than just good facts to know. And in particular, the first four parts actually do give you an algorithm to compute determinants, even in high dimensions. Here's the algorithm. Row reduce the original matrix to row echelon form, not necessarily to reduced row echelon form. I mean, you could go to reduced row echelon form, but you don't need to. Keeping track of row operations along the way. Compute the determinant of that row echelon form, which will be an upper triangular matrix, that's guaranteed. That determinant by the theorem is the product of the entries along the main diagonal. That's easy to compute. Finally, use the theorem parts B through D to compute the determinant of the original matrix. Work backwards, so to speak. If you did any row switches, then you multiply the determinant by -1. If you do row replacement operations, the determinant is unchanged. If you multiply the matrix times a row of the matrix by a constant, non-zero constant, then that does change the determinant. So you have to be tricky there, or careful there. It is a bit silly to use that for a 2x2 matrix, but I'm going to go ahead and do that anyway, just to illustrate the method. Here's a 2x2 matrix. I am also going to illustrate it for a 3x3 and 4x4 later. Here's a sequence of row operations that gets to an REF of A. Here's A here. Here's a row echelon form of A. That's an upper triangular matrix. Its determinant is -4, 1 times -4. I did have to, this is a row replacement operation there. This is a multiplication by a non-zero constant. I do have to take this one into account. This one doesn't change the determinant. And here are the computations. The determinant of A would be 2 times the determinant of B because I had to multiply the first row by 1/2. So working backwards, the original matrix is 2 times the determinant of the new matrix. So it's 2 times -4, which is -8, and you can obviously check that by just doing 2 times 5 is 10, minus 18 is -8. What was our original motivation for the determinant? And this motivation, the idea of reviewing this, is it does generalize to higher dimensions. Back in section 1.3, we wanted a condition on which a general 2x2 system like this with 2 equations and 2 unknowns has a unique solution. And back in that section I said it's got this unique solution if and only if AD minus BC is non-zero, because otherwise you'd be dividing by 0 here. And that quantity, AD minus BC, is the determinant of the 2x2 coefficient matrix. 2x2 matrix with entries A, B, C, and D. Okay. For higher dimensions, we want to define the determinant so that that fact generalizes. In other words, we want to still be able to say that for a system of n linear equations and n unknowns, it's got a unique solution if and only if the determinant of the coefficient matrix is non-zero. Here is the formula for a 3x3 matrix, and what I'm about to do is show you where this formula comes from now, in a sense, by doing the row operations and on the coefficient matrix and thinking about when we would actually not have a unique solution, This is not a complete proof, but it's just a derivation. So here's your arbitrary 3 by 3 system, 3 equations, 3 linear equations, and 3 unknowns. If I put all these numbers, A, B, C, D, E, F, G, H, I, and also U, V, W in a matrix, that's called an augmented matrix. I have talked about that before. And that would actually help you solve the system if you wanted to know the solution. But we don't want to know the solution here. We want to just know if there is a unique solution. So instead of looking at the augmented matrix, we can look at the coefficient matrix, where we just look at the coefficients of x, y, and z, a, b, c, d, e, f, and g, h, I. That's going to be a 3 by 3 matrix. And we want to go to reduced echelon, just row echelon form, which will be upper triangular, and then use the algorithm to compute the, or to think about, actually it's not an algorithm to compute the determinant. We're going to think about when this would not have a unique solution. That's the goal here. Okay, so let's look at the row operations in the coefficient matrix. I'm going to assume for convenience that we're never dividing by 0 in the midst of this computation. That's going to assume in particular that A is non-zero. And therefore the case where A is 0 would have to be handled separately. Here are the details. Now I'm not going to check all these things for you. This is a place where maybe you want to pause the video and double check all these things. It's a bit messy, especially in the very last step here, but that is the computations that if we implicitly assume we're never dividing by 0, this would be the REF of the original matrix. And what's the key now? Now remember, this corresponds to an equivalent system of equations for the original system, where if I was trying to solve the original system, I'd also be doing these same row operations with the fourth column of the augmented matrix. Remember that we have unique solutions when this thing would also be a non-zero number. So it's not going to be a unique solution if this thing right there is 0 in the lower right corner of that matrix. I'm also assuming I'm not dividing by 0 here. When would this not have a unique solution? When this thing is 0, when the numerator of this fraction is 0. That's what I say right here. That's the numerator of that fraction right up here. Let's go ahead and simplify this, see what it is. If you expand it with algebra, you get this. And it turns out you can factor out an A there and get this. And since in this case we're assuming A is not 0, again the case where A is 0 would have to be handled separately, we can ignore the A and we can just focus on this thing being 0. But that thing is the same as the determinant of the original system, amazingly. Okay, so you got to check those computations to appreciate this all, but it does work, at least in the case where A is non-zero. So that's a lot of algebra. The next section gets back to geometry. Visuals that are, I hope you think, beautiful. Can you geometrically interpret 3 by 3 determinants of 3 by 3 matrices? Yes, you can. Let A be a 3 by 3 matrix with columns U, V, and W in that order. In other words, you could write A symbolically like this, U, V, W. If this ordered list of vectors is oriented according to something called the right-hand rule. Now at this link there's a picture of it. Though I will tell you this in this picture from Wikipedia here, they introduced something else called a cross product. They've got 3 vectors here, A, B, and this third vector, that's their cross product that I'm going to call C. You could think of these in my setup as being the vectors U, V, and W, with, I can do this here for you. U being where you're pointing with this finger, V being where you're pointing with this finger, and W being where you're pointing with your thumb. If the vectors are oriented to be able to follow that picture, then that satisfies something called the right-hand rule. And that's what I'm showing in this picture here. You sort of imagine this with 3 dimensions. U is, again, with your pointer finger, V with your third finger, and W with your thumb. Those do follow the right-hand rule. They match the orientation of your right hand, not your left hand. And in that case, the determinant will be positive, and it will be the volume, not an area, a volume of this object spanned by these vectors, or determined by these vectors in this picture here, this 3-dimensional slanted box. It's got a name, a cool name. It's called a parallelepiped. I think that's how you pronounce it. Kind of a fun word to say. Parallelepiped. The determinant of the matrix, this matrix here, will be positive in this situation and will be equal to its volume. Now, if it's not oriented according to the right-hand rule, if it's oriented according to the left-hand rule, then the determinant would be negative and its absolute value would be the volume. You can think of this in terms of linear transformations as well. Just like before, the volume of the image will be the absolute value of the determinant times the volume of the original set. And if you think of it in terms of signed volume undergoing some sort of flipping, in higher dimensions, the signed volume of the image will be the determinant without absolute value signs times the volume. I do have a visual for this in this example. I did make a little visual. We can illustrate this for this 3x3 matrix. Its determinant is -3, so somehow under the linear transformation, the sets will undergo some sort of flipping. Here's the row operations to confirm the determinant is also a -3, confirming the theorem in the 3x3 case. And here we see a visual showing how the original three vectors, these three right here, u, v, and w, that do follow the right-hand rule, when you look at their images, t of u, t of v, and t of w, they don't follow the right-hand rule any longer. T of w is kind of coming out of the screen at you there a little bit. Excuse me. They follow the left-hand rule, oriented according to your left hand. You might want to try with your right and left hands here to double check that. And if we made the parallelepipeds that these spanned, it would undergo some sort of flipping. I guess I could have tried to make that here, but I didn't. And you'd think about the image parallelepiped as having a negative signed volume. So that's undergoing a flipping, essentially because the green vector is sort of changing its overall orientation with respect to the red and blue vectors that are not really changing their orientation with respect to each other. That's a lot to think about. All right, take a breath. We're getting close to being done here. On to high dimensional determinants. If n is greater than 3, the most common way to compute a determinant is via the so-called cofactor or Laplace expansion across the first row of A. In the case of a 3x3 matrix, we can note that in this formula here, EI minus FH, this thing right here, DI minus FG, this thing right here, and DH minus EG, this thing right here, are actually determinants of 2x2 submatrices of the original 3x3 matrix. This matrix is found by deleting the first column and first row of the original. It's right here. This matrix right there is found by deleting the first row and the second column, DG, FI. Those four numbers are now in this 2x2 matrix. And this 2x2 submatrix is determined by deleting the first row and third column to get this matrix right here. Those expressions are determinants of those submatrices, where you use coefficients of those determinants A, B, C, alternating in sign, plus, minus, plus. Okay, that kind of pattern carries over to higher dimensions, and it's called again, the cofactor or Laplace expansion across the first row. I'm using the first row A, B, and C as the coefficients with this plus, minus, plus as well. Building on this idea, we can say what to do in the 4x4 case. The determinant of an arbitrary 4x4 matrix like this, we expand across the first row with the coefficients A, B, C, and D, and the signs alternating plus, minus, plus, minus. And these things are getting multiplied by determinants of submatrices. A11 is the submatrix obtained by deleting the first row and first column to get this submatrix. For example, A13 is obtained by deleting the first row and third column, to get these two as the first two columns of the submatrix, and this one over here as the third column is what you see down here. And that is how to calculate the determinant in the 4x4 case. And this pattern can extend to higher dimensions to do 5x5 and 6x6 matrices, etc. But the computations, as you can imagine, become very laborious. That's definitely true, even for a computer. It can take computers a long time to compute determinants of even, I don't know, 20x20 matrices. Okay, that could take a long time even for a computer if you're using this method. Because, for example, the determinants of these matrices are kind of complicated as well. Those are all 3x3 matrices. Okay, I go ahead and do an example here. I do use an alternative notation for the determinant here that's a little bit confusing. I call it absolute value notation here. It is a common notation for the determinant. It's just more convenient here. But determinants definitely can be negative, though. Don't let this make you think determinants must be non-negative. They can be negative, as they are in this example. This determinant is negative 51. You should double check all these calculations. I'm expanding along that first row with coefficients 1, 3, 0, and negative 2. 1, 3, 0, and negative 2. I didn't put the matrix next to the 0 because I didn't need to, but I have determinants of submatrices here, here, and here. And you should check all these calculations. And here I did check it with the REF algorithm. And I made it easy on myself by only doing row replacement operations, so the determinant is unchanged. You get the same answer, negative 51. It's very satisfying to see that. This does have a geometric interpretation as well. In fact, in n dimensions, it's got a geometric interpretation. But it's not a geometric interpretation you can literally imagine, because we can't imagine beyond 3 physical dimensions. But if you've got a subset of Rn, that's nice in some sense. There is an n-dimensional volume or hypervolume that can be defined, but again, that's a topic for measure theory. Just think intuitively, like a 4-dimensional cube, for example, would be the product of the lengths of the 4 independent sides, you might say. Okay, it can be defined. The volume of the image, the hypervolume, n-dimensional hypervolume of the image is the absolute value of the determinant of the matrix times the n-dimensional hypervolume of the original. And you can think of this in terms of signed hypervolumes. That gives you a negative answer when the determinant of the matrix is negative. The absolute value of the determinant is also an n-dimensional hypervolume of an n-dimensional parallelepiped, which you can't imagine, but it can be defined by this expression right there, the set. A linear combination of the vectors that are in the columns of the matrix. In the case where the determinant is 0, and I guess I forgot to mention this earlier, then T is degenerate and maps sets with positive hypervolume to sets with 0 hypervolume, and that applies to the 2- and 3-dimensional case as well. Final thing here is just to look at a few other applications of the determinant. The main application we will use is this one here, at least right now. The system of n linear equations and n unknowns has a unique solution if and only if the determinant of its coefficient matrix is non-zero. Furthermore, if the determinant is 0, the system will either have no solution or infinitely many solutions. There's something called Cramer's rule here that you can look at and think about if you want. You can explore it if you like. It's not so useful these days. People don't typically use it, but historically it was fairly important. You can look this over and also click on this link to check more about Cramer's rule. Finally, in Chapter 3 of my online textbook, which I'll get to sometime next year, determinants are important for computing what are called eigenvalues of a matrix. And that has applications to, as we will see in Chapter 3, to differential equations and difference equations, is what I say here. Differential equations related to calculus, difference equations you can do without calculus. Okay, so those are some applications, and then I just got a few exercises so far. I will probably add more in the future. Thanks for watching.